Hi there. How you doing? Welcome to Linear Algebra. This is our first unit. It's the introduction to vectors and linear combinations. Let's go ahead and get started. So our definition is straightforward. A vector in Rn is simply an ordered list of n real numbers. The n that's in this part of the definition also shows up here. And what that means is that once I choose a value for n, it replaces in both times. So if I were to say, for example, a vector in R2, then what I mean is something like the vector with two real numbers in it, like 2, -7. And if I were to say that I had a vector in R3, then I'm talking about a vector with three real numbers in it, like 3, -5, and -6. So the n here corresponds with the actual number of entries in the vector. So as an example, all of these are vectors in R2. In R2 we have vectors that include -6, 3 and 11, 4, 11.4. This is vector W. Vector X has not been simplified yet. I could reduce cosine of pi over 6 to square root of 3 over 2 and sine of pi over 6 to 1/2. But regardless, these are still real numbers, and therefore this is a vector. In print, we will use bold letters to identify vectors, and we will choose to write vectors vertically instead of horizontally as the way that we present our list. We say that the numbers that are inside the vector, in this case -3 and 1, are the components of the vector. If I want to plot a vector, there are a couple of ways of doing this. This is the vector v, which starts at point A and ends at point B. So the starting point is called the tail of the vector. The ending point is called the head of the vector. The ending point is called the head because it lines up with the head of the arrow. So the starting point is the tail, the ending point is the head, and the coordinates tell us how to get from A to B traveling in the x and the y direction. So in the x direction, we have to go 3 units to the left. And the y direction, we have to go 1 unit up. And that gets us from point A to point B, and so this is the vector -3, 1. Then the vector W, P and Q are further apart in this example. To get from P to Q, I first could travel horizontally 4 units, and then vertically I'd have to travel another 3 units. And that gives me the vector 4, 3. This way of plotting vectors means that two vectors could have exactly the same coordinates even if they're in different locations in the plane. In this example, J, from J to K, is 3 units to the left and 2 units up. And the vector from S to T is 3 units to the left and 2 units up. And so both vectors have the same coordinates, -3, 2. And so we say that the vectors are equal to each other. Vectors can be equal even if they're in different locations. They don't have to be in the same place to be equal. They just have to represent the same amount of movement in the x direction and the same amount of movement in the y direction. Or in if we're in R3, then also the same movement in the z direction. We've seen the vector 4, 3 before, but let's look at it again. This is a vector that moves 4 units in the x direction and 3 units in the y direction. And the x and the y direction are perpendicular to each other, so this forms a right angle. You might recognize this as a 3, 4, 5 right triangle, and that tells us that the length of v is 5 units. We could check that out by using the Pythagorean theorem. A squared plus b squared equals c squared. So the hypotenuse is the square root of 4 squared plus 3 squared. We say for any vector that the magnitude is the length of the vector, and it has the value the square root of the sum of the individual coordinates squared. The notation for the magnitude is that looks like double absolute value bars. So we've done an example already. The magnitude of the vector 4, 3 is equal to 5. But we could do another example here. Let's find the magnitude of the vector 4, 7, negative 4. That would be the square root of 4 squared plus 7 squared plus negative 4 squared. And that's the square root of 16 plus 49 plus 16. And those add up to 81. The square root of 81 turns out to be 9. And so the magnitude of this vector is 9. Adding vectors works out as nicely as you could expect. As long as the two vectors have the same number of entries, that's a way of saying that they're both in R2, or they're both in R3, or they're both in R4, then we add the vectors just by adding the entries in the corresponding positions. As an example, if v and w are the vectors 3, 6, 1 and 2, negative 4, 3, they are both in R3. So they both have the same number of coordinates. V and W together add up to 5. 3 plus 2 is 5. 6 minus 4 is 2. 1 plus 3 is 4. And so V plus W is the vector 5, 2, 4. Visually, if we wanted to graph a sum of two vectors, let me show you this example. We could add these two vectors v and w by starting at the origin, traveling along the vector v, which is 2 units to the right, 3 units up. And that's where v takes us. And then starting at that point, and not going back to the origin, but starting where v left off, we'll travel along the vector 4, 2. 4 units to the right and 2 units up, and that's where w takes us. And so combined, v and w together takes us from the origin all the way to this point, which is 6 units over in the x direction and 5 units up in the y direction. And so this is the vector 6, 5. We call this the head-to-tail rule because the point where the two vectors that we're adding together meet is the head of vector v, but it's also the tail of vector w. And so we line up the head of one vector with the tail of the other vector. And that's how we can visually represent the sum of two vectors. Another straightforward operation that we can do with vectors is to multiply a vector by a constant. When we do this, we scale the entire vector, and every coordinate of the vector gets multiplied by that same constant. This example is in R4. X is the vector 2, 1, negative 3, 8. And we're going to multiply the entire vector by 6. That means the x coordinate and the y coordinate and the z coordinate and whatever letter comes after z all get multiplied by 6. And so the vector 6x is 12, 6, negative 18, and 48. Visually, multiplying a vector by a constant changes the size of the vector. This is the vector 1, 1, just 1 unit over and 1 unit up. When we multiply it by 3, 3v is the vector 3, 3. It's now 3 units over and 3 units up, so it's 3 times as long as it used to be. But it's still pointing at a 45-degree angle to the origin. The angle didn't change, only the size of the vector. But multiplying a vector by a negative number, this is now the vector negative 2, negative 2, that does change the direction of the vector, but it changes it by exactly 180 degrees. The angle is now an angle of 225 instead of 45 degrees. So when we multiply by a negative scalar, the vector reverses direction. A unit vector is any vector whose magnitude is exactly equal to 1. And we can find a unit vector parallel to any vector, any non-zero vector, by first finding the length of that vector and then scaling the vector by 1 over that magnitude. I'll show you an example. This example is a little complicated, so in the next slide I'm going to present a type solution. But we'll do this out by hand first. This is vector negative 2, 4. That's negative 2 units to the left, 4 units up. And that vector crosses the unit circle at a point P. The unit circle has a radius of 1. And so point P is only 1 unit away from the origin. And we would like to find the vector that goes from the origin to point P. We would like to find the coordinates of this little vector here. So the first thing we're going to do is we're going to find the magnitude of the vector v. This is the Pythagorean theorem. It is the square root of negative 2 squared plus 4 squared. That's the square root of 4 plus 16, which is the square root of 20. That number is approximately 4.5. So it tells me right now the vector is 4.5 units long. So if I want to shrink it down to 1 unit long, I'm going to have to divide everything by 4.5. I'm going to have to divide everything, in this case, by the square root of 20. And so my unit vector that goes from the origin to point P is the vector negative 2 divided by the square root of 20 and positive 4 divided by the square root of 20. And as promised, this is the same solution we just found. The magnitude is the square root of 20, and so we have to divide everything by the square root of 20 to obtain a unit vector. The unit vector we want is negative 2 over the square root of 20 and 4 over the square root of 20. Let's try another example. Let's find a vector that is in the same direction as 4, 7, negative 4. So the first thing we're going to do is find the magnitude. So the magnitude of v. We did this problem earlier, if you remember. This is the square root of 4 squared plus 7 squared plus negative 4 squared. And that turned out to be the square root of 81, which is 9. And then we're going to divide every coordinate of v, every component of v, by the magnitude of v. And so that gives us the unit vector is going to be 4 over 9, 7 over 9, and negative 4 over 9. And that's our answer to this example. All right, let's move on. So another definition. We want n to be any positive integer greater than or equal to 1, and we're going to have a set of vectors that are in Rn. We say that a linear combination of those vectors is any new vector that can be written in the form of a sum of multiples of v1 and v2 and all the way up through however many vectors we have. The multipliers that we have in the linear combination, they're called weights. I'll give you an example on the next slide. The vector 13, 3, 19 is a linear combination of these two vectors. I'll call these vectors A and B. A is negative 1, 4, negative 8. B is 2, 3, negative 1. And the combination that we have is to take negative 3 copies of A and 5 copies of B. Negative 3 times the first vector and 5 times the second vector. And that gives us 13, 3, 19. We can check that. In the top row, in the x-coordinate, we have negative 3 times negative 1 is positive 3, plus 5 times 2 is 10. In the middle row, we have negative 3 times negative 4 is negative 3 times 4 is negative 12. 5 times 3 is 15. And negative 12 and 15 is 3. That checks. And in the bottom row, we have negative 3 times negative 8 is 24. 5 times 1 is negative 5. 24 minus 5 is 19, and so that checks. And so using the two starting vectors and the two operations we talked about earlier, addition and scalar multiplication, we were able to combine those two vectors into a new vector, 13, 3, negative 19. Sometimes this process can't work. I cannot build the vector 3, negative 7, 8 as a combination of the three vectors shown here. These three vectors, no matter how we combine them, we're always going to get a 0 for the middle component. Any number times 0 is 0, and any sum of zeros is going to be a 0. And so it is not possible to build a vector with a negative 7 for the y-coordinate out of vectors that only have zeros for the y-coordinate. And so it's not possible to build a linear combination of v1, v2, and v3 that equals 3, negative 7, 8. So not all vector linear combinations are possible. This one is not. On the other hand, sometimes a linear combination is possible in two different ways. Here's an example. The vector 1, negative 7 is a combination of these three vectors, 1, negative 1, 4, 2, and 6, 0. One way is to take the first vector times 3, and the second vector times -2, and the third vector times 1. Let's check that out. 3 times the first vector is 3, -3. -2 times the second vector is -8 and -4. And the third vector is 6, 0. And when I add those together, 3 plus -8 is -5. -5 plus 6 is 1. And the y-coordinate, -3 plus -4 is -7. -7 plus 0 is still -7. And that is our vector v. So that vector is a linear combination of the other 3 vectors. But it's also this linear combination. Let's try this. v1 is 1, -1. -3 v2 is -12 and -6. Positive 2 v3 is 12 and 0. And when I add these together, I get 1 minus 12 plus 12. The minus 12 and the plus 12 cancel, and I just get 1. -1 minus 6 is -7. -7 and 0 is -7. And that also equals v. And so this vector is a linear combination in 2 ways. We'll talk more about that in just a moment. Here's a visual example of a vector that is a linear combination in 2 ways. This vector v has the coordinates 4, 2. That's 1, 2, 3, 4 to the x direction, and 1, 2 up in the y direction. So one way we can build this vector is to start along the diagonal direction v1, travel along this diagonal direction for 2 copies of v1, and then once we get to this point, turn and move horizontally in the v2 direction for 2 copies of v2. And so that gives us a combination that v is 2 times v1 plus 2 times v2. Another way of building v is to start at the origin and take, instead of 2 copies of v1, take 4 copies of v1. Now instead of being to the left of v, we're above v. And so we have to move downwards, and downwards is the v3 direction. We'll move 2 copies of v3. And so v is equal to 4 times v1 plus 2 times v3. And so using v1 and v2 and v3, we can build v in 2 different ways. This next theorem is a little complicated, but I'll walk you through it. We're going to start out with a set of vectors that are all in Rn. That means all of the vectors in our set have the same number of components. And we have a vector that is a linear combination in 2 different ways. So we've already seen 2 examples of a vector that is a linear combination of another set of vectors in 2 ways. The next part of the theorem just re-explains what it means to be a linear combination 2 ways. It says, that is, there exist scalars. These are the weights in the first combination, and then these are the weights in the second combination. And so this is our first combination. And this is our second combination. Our theorem says, if we have a vector that's a linear combination in two directions, then, here's the important part, then we can do this next process for any real number t. For any real number t, I can multiply the first combination by t and the second combination by the number 1 minus t. So this is t times combination 1. Actually, I'll type this out. So this is t times combination 1 plus 1 minus t times combination 2. And that will be a new combination that is also equal to v. And because we can do this for any real number t, v is a linear combination in an infinite number of ways. Not just two ways, but an infinite number of ways. That should be exciting. What implications this has for engineers and builders and designers and creative people is that as soon as you have identified two ways of building a linear combination, those two ways open up an entire spectrum of combinations from which then you can choose a linear combination that optimizes for some priority of yours. Which linear combination would be cheapest to build? We have an infinite number to choose from. We can choose the one that is the cheapest. Or which one is the most energy efficient? We have an infinite range to choose from. We can choose the one that's the most energy efficient. Or which one can we build in the fastest time? We have an infinite number to choose from. We can identify the one that we can build the most quickly. That once you can find two solutions to a linear combination problem, you have an infinite number of combinations, and that gives you a bunch of different ways that you can customize the solution to your problem based on what your priorities are. And so this is going to be a big deal for us, and it's going to be our focus for the next couple of weeks, is solving these problems that have an infinite number of solutions. In the next slide, I'm going to give you an example. Let's look at this example. We can write the vector 5, negative 1 as a linear combination of these three vectors, which I'll call A, B, and C, in two different ways. 5, negative 1 is 2 times A plus B minus C, and it's also equal to negative A plus 4B plus 2C. And our goal is to find another linear combination that also adds up to 5, negative 1. And so based on our theorem, we can pick any number we want to for t. In this example, I'm going to use the number 3. And then we're also going to use the number 1 minus t. And 1 minus 3 is negative 2. And the rule says to multiply the first combination by t. So that's t times combination 1. And negative 2, 1 minus t, times the second combination. And so if we multiply the first combination by t, then instead of having 2a, we're going to have 6a plus 3b minus 3c. And we're going to multiply the second combination by negative 2. Minus times negative 2 is going to be plus 2a. 4 times negative 2 is going to be minus 8b. And 2 times negative 2 is going to be minus 4c. When we combine those together, 6 and 2 is 8a. 3 and negative 8 is minus 5b. And negative 3c and negative 4c is negative 7c. And my claim is that this combination will also add up to the vector v. So let's check that out. That's 8 times 3, 1. That's 24, 8. Negative 5 times 1, 1 is negative 5, positive 5. And negative 7 times 2, 2 is negative 14 and negative 14. And when we add these together, 24 minus 5 is 19. 19 minus 14 is 5. 8 plus 5 is 13. 13 minus 14 is negative 1, and that does indeed equal v. So that checks out for us. Once we have two linear combinations, then we can use this t and 1 minus t trick to generate an infinite number of linear combinations. We're going to wrap up with a simple definition, and then, like I said, we'll wrap up. In R2, we define two special vectors. E1 represents moving 1 unit in the x direction only. And E2 represents moving 1 unit in the y direction. In R3, we'll define three vectors, E1 and E2 and E3, representing 1 unit in the x direction, 1 unit in the y direction, and 1 unit in the z direction. And in fact, we'll extend this definition however necessary, so that if we're in R15, we'll have 15 of these vectors numbered E1 through E15. We call these the standard basis vectors. And the very nice thing about these standard basis vectors is they're very easy to compute with, because you're only computing with ones and zeros, and those are some of the easiest numbers we have. I'll show you a couple of examples. Let's find the component of the vector in R3 that's equal to 5e1 minus 6e2 plus 2e3. Well, e1 is 1 unit in the x direction, and E2 is 1 unit in the y direction, and E3 is 1 unit in the z direction. And so when we combine these, we get 5 times 1, which is 5, minus 6 times 0 plus 2 times 0. In the y-coordinate, we get 0, which is 5 times 0, minus 6 times 1, which is minus 6. 2 times 0 is 0. When we add those together, we get minus 6. In the z direction, we get 5 times 0 minus 6 times 0. That's 0. Plus 2 times 1 is 2. And it turns out that the components of the vector are exactly the same as the coefficients in our linear combination. I'll do one more example. Let's write this vector, 4, negative 2, as a linear combination of E1 and E2. Well, that's just the vector 4 times E1 and negative 2 times E2. E1 is going to be 1, 0, so when we multiply that by 4, we get the 4 in the top row. E2 is 0, 1, so when we multiply that by negative 2, we get the negative 2 for the bottom row. And so these linear combination problems are very quick and very easy to solve using the standard basis vectors. That's going to give us a technique that we're going to look at next time, where we'll take a linear combination problem in some complicated set of vectors and turn it into a linear combination problem in standard vectors. And that one will be easier to solve than the original problem. We'll look at that next time. Thank you for staying through the video. I'll see you soon.